So thanks a lot for the invitation. This is my first ever Palas, because a bit of a confession, I'm not actually a paleontologist. Please don't throw me out. So what I said I would talk about today is some work that we've been doing looking at time slicing or time subsampling in disparity through time analyses. And I should first of all acknowledge Thomas. So Thomas Guillerme is based in the University of Queensland at the moment, but we started some of this research when he was doing his PhD with me. He's still continuing to work on this quite a lot. He's running a disparity working group in January, so watch this space if you're interested in disparity analysis and sort of ways of linking those things together. So Thomas is the person who did all the implementation of the code. So the places where the cake looks more like this is my coding, so apologies. So yeah, like I said, I'm not a paleontologist, but most of my research is phylogenetic comparative methods, macroecology, and macroevolution. And so one of the things I think we're very interested in, both as paleontologists and neontologists, are these ideas of diversity and morphological diversity as well. So when I'm saying disparity here, I'm talking about morphological diversity. And part of the reason we're more interested perhaps in disparity than diversity sometimes is because we're interested in sort of the morphological variation which may account for differences in ecological niches and how species actually interact with each other and their environments. And so these are just some of the things we're working on in my group at the moment. But one thing that we're really interested in is how you can use neontological and paleontological data together, and also how you can use methods from both fields to sort of inform what's going on in these kinds of analyses. But mostly when we're talking about disparity, we're really interested in disparity through time. So we're interested in looking at our clade and seeing how disparity might have changed through the history of that clade. And we may just be interested because it's cool and we love our clades so much, but we may also have some really interesting biological questions to ask with this. So we may be interested in knowing what happens during and after a mass extinction event to disparity. Or we might be interested in competitive replacement. So when we see one clade kind of taking over the morphological space of another, even though they may not be very closely related. So this is a methods talk, obviously, so I'm not going to talk about any nice, cool biology. It's just going to be fun methods from now on, so it's the point where everybody gets up and leaves. But there's two aspects to a disparity through time analysis. Now, I wasn't sure what Graham was going to talk about this morning, so you'll see there are some bits which maybe don't have as much explanation as perhaps are needed. But essentially, I'm going to completely avoid talking about how we measure disparity because it's a statistical can of worms. I've been talking to some statisticians about this recently, and they're absolutely horrified when I tell them about how we actually summarize multivariate space. So for now, let's just ignore how we're measuring disparity and just say that it's a kind of diversity metric. We're taking multiple taxa and then looking at their morphology and getting some individual number out of that to get some idea of how diverse the morphologies are in that group. The other part of this, and this is what I'm going to focus on, and unfortunately I've forgotten that the Imperial uses PCs, so just imagine that this is moving. So yes, it's great. So what we're really more interested in is the through time bit, and that's not just so I could use this cute GIF. So up on these slides, I'm going to have time in millions of years on the bottom, and then just in case anybody's forgotten, we've got the present day at one end and a sneaky Star Wars joke just for Graham that a long time ago is at the other side there. And so what we're generally, then this is my, this is just because I'm going to put some bird pictures on here, and I don't want anyone to come up to me afterwards and go, that's not the relationships between birds. I know these were just the only philo pics I had on my computer when I was making this thing. So these are made up data. Please don't panic that I'm rewriting bird phylogeny. So what we're suggesting here is that normally what we're going to have is through the history of our clade, so we've got time here, and we've got some kind of, some taxa being discovered through time. We might be interested in how the disparity of that clade is changing through time. And so these are our taxa that we've got. We've got some which are extinct, and we've got a few which are still existing in the present day. Now, of course, the problem with this is, as I was saying, disparity is a diversity metric, so you need more than one individual in order to be able to actually calculate a disparity score. So what we need to do is think of a way of subsampling our taxa in order to get these disparity measures. And the common way that people will do this is by using stratigraphic time bins. So these are generally unequally sized. They might be ages or epochs, whatever your favorite period might be. And so in that, what we would do is just plot those the stratigraphy against our taxa, so our first and last occurrence dates, split it up into those groups, and then we'll have these time bins, or these groupings, these subsamples of species that we're then going to calculate disparity for. So in this case, we'll calculate disparity for the penguin and the thrush, then for the kiwi, and then for these 3 species in period 3. We plot these usually on a disparity through time graph, so we've now got disparity up on the oh, I can use the thing. Sorry. I've only just worked out how this works. The disparity is on the y-axis here. So we're plotting disparity here. And then generally, because we like to look more robust, we'll put some error bars on this. And so this is done through bootstrapping. So we get these bootstrapped error bars on our disparity. Again, this is something that makes my statistics friends cry, but we'll not talk about that today. So the problem with using this method is that just by chance, bigger bins are likely to have more taxa within them, and therefore more likely to have these extreme morphologies and larger disparities. So we're going to have some kind of bias related to the amount of disparity that we have depending on the size of the bins. We can try and fix this with rarefaction, but if we have some time periods with very few species, we can end up with really big error bars, which makes it really difficult to actually test any biological hypotheses sometimes. Often we don't have much power. So one solution, and this is a really commonly used solution, is to use equally sized time bins instead. So often people will kind of fudge together. So rather than perhaps having completely equally sized bins, you can kind of make some of your stratigraphic periods slightly smaller or bigger in order to get roughly equal sizes. Or you can use things like taking the time frame that you're interested in, working out what the average duration of a stratigraphic period is within that, and then using that as your time interval and just splitting up the time in that way, or by doing it by the average number of stratigraphic periods and just splitting it up that way. And so just to kind of follow through, this is the way that would work. So instead, we've got these bins. And so here we've got vaguely equally sized bins, and we've got different taxa falling within those. And again, we can go away and calculate disparity for each of those. Excuse me. I'm also just recovering from a cold, so it's a little bit touch and go whether my voice will last till the end of this talk, so it could be quite exciting. So again, we're going to put on these error bars from the bootstrapping, and we've got our disparity through time. Now, there are some problems with this, and some are fairly obvious, and one is perhaps less obvious. So then probably the obvious problem is that we're often limited by the number of taxa that we actually have in each of these stratigraphic bins. So in this particular example, as I said earlier, we can't actually calculate disparity when we've only got one individual. So although I've sort of shown you this kind of plot to sort of make this easier, actually all that we would be able to do in this example is have one disparity calculated. Now, of course, if all the interesting stuff in your clade is happening back here, all the interesting changes in climate or things like that you might be interested in testing, then you're not really going to be able to say anything using this particular data set. Oh, sorry. Another problem, which is perhaps less obvious, is that each of these time subsampling approaches, so whether you've got, each time binning approach, whether you've got equal or unequal bins, you're assuming a punctuated model of evolution. So we do agree that that happens in some taxa, but it's not going to happen all the time. So if you're only assuming that changes happen at the boundaries of these bins, then you're making an assumption of punctuated evolution. You're not allowing there to be gradual change in characters through time. And that may or may not be a problem depending on the clade that you're using. Luckily, though, we've got a good way of solving this problem, and a lot of talks have already sort of brought up phylogenies, in that a lot of groups now will have a phylogenetic tree, and if we've got a phylogeny of our group, then we've got a bit more information about what's going on. So we know, for example, in this time bin at the end, where it looks like we've only got a penguin, actually we must have something here about the ancestors of the rest of this group. There must have been some ancestral species existing here, or these guys wouldn't exist either. So the phylogeny is giving us a little bit more information about the kinds of taxa that might exist. And this, I think, comes back to some of Graham's points when he was looking at his phylomorphospaces and the information that we were ignoring when we look at those. We've also got ancestral species in there. So the nodes we can think of as being the ancestors of these groups. And we know that there are going to be ancestral species within these time bins, which up until now we've been kind of ignoring. So our solution to this problem then is what I'm referring to as a new-ish method, which we're calling time slicing. It's new-ish because there are a number of people in this room who have either used a very, very similar method in the past, or certainly proposed a similar method and maybe not implemented it. So essentially all that we're going to do is, rather than taking bins, we're going to do something similar again. So maybe afterwards, if people are interested, we can talk about how this differs from Graham's stochastic character mapping approaches. But we're going to again take these time slices through the phylogeny, and instead of selecting what's in the bin, we're going to select where this time slice crosses. So either the tip taxa, or the ancestors, or whatever's going on at the branch. So how do we do this practically? We gather together a bunch of data. So we're going to get the time-scaled phylogeny for the group. We're going to take a morphological matrix in these examples, I'm just using cladistic data, similar to what we've seen in a few of the previous talks. But you could also use morphological measurements if you wanted to. Any kind of ordinated data can be put into the R package. And also first and last occurrence states for all of the taxa. The first thing we need to do is reconstruct ancestral states following the same terminology that Graham was using. We're using ancestral state reconstruction before ordination, so the pre-ordination techniques. And this actually uses code from Cladis, which is Graham's R package, which should be cited up there, but it's fallen off the end somewhere. So we reconstruct those ancestral states using a rerouting method. And so then what we've got is, in this cladistic matrix, we've not only got the character values for the tip species, but also for whatever's going on at the nodes, so these ancestral species too. We then throw it through an ordination. In this case, we're going to use PCO or MDS, so principal coordinates analysis or multidimensional scaling. These are the same thing. They've just got different names in paleontology, ecology, evolution. There's like a mixture between fields, but they're the same approach. And so all that's doing is same as any ordination, same as a principal components analysis, just rotating that data so that you end up with the major axes of the variation as what we've got. And then we end up with these ordination scores for all of the things which are involved in our phylogeny. So we've got ordination scores for the nodes, and we've got ordination scores for the tips. So we're going to take those time slices then. So these are going to be equidistant through the phylogeny in the same way as we would do for time bins, probably related to something like the average duration of a stratigraphic period within the time frame of interest. And then we're going to take the values for either the tips, or the nodes, or the branches, so taking those ordination scores, and then we're going to use those to estimate disparity at each time point. So the astute among you have probably noticed that I said we have ordination scores for the nodes and for the tips, but I'm saying that we're going to select values for the branches as well. And so this is where our method slightly differs from previous methods. And so we've got 6 different ways that we can actually select what the value should be at a branch. Some of these are easier than others. So the first one is an ACTRAN method, an accelerated transition, assuming that transitions happen early on a branch. Therefore, every time, if we have a slice here on this branch, we're going to always take the value for the descendant here. And at the moment, I'm showing this as a tip species, but this could equally be another node. So they're just ancestors and descendants relative to where they are on the branch. You can also use a Deltran method, which is the opposite, where you always pick the ancestor. You can use a random method where you randomly choose one or the other, or you can use a proximity method where you choose whichever is closest to the time slice. In this case, it would be the ancestor. Now, all four of these methods are still punctuated methods, so punctuated evolution models. And the other important thing is that they're only going to choose one value once for each of these time slices, for each of these branches, so only one choice. These other two methods, on the other hand, are gradual change models. And instead of just choosing just one value for the branch, they're going to take a distribution of values based on where the slice occurs. And so the distribution of values can be taken during the bootstrapping. So in the equal splits, for example, in 50% of the bootstraps, you select the value for the ancestor. For 50% of the bootstraps, you select the value for the descendant. And then the most complicated model is this gradual splits model, which is based on where the slice occurs. In this example, we have a slice occurring 75% of the way along the branch. If we're assuming that there's a gradual mode of evolution, then we're assuming that things are probably closer to this one than to this one, in which case we're going to take 25% of the bootstraps from the node and 75% from that tip value. Okay. So that's where we get these branch values from. We're going to take our time slices, estimate disparity, get the bootstraps, and then we've got a nice disparity through time plot going on there. So that's the kind of the end of the method. It's fairly straightforward, I hope, anyway. So all of the code for this is available in Thomas's GitHub. So this is an R package called Disparity. There's lots of other stuff in there as well about using different kinds of models different kinds of metrics to estimate disparity. It's currently slightly in flux because it's in revision, but it's going to be hopefully published in Methods in Ecology and Evolution fairly soon. But that's kind of, I'll put this link up again at the end if people need it. So just what I wanted to kind of throw up here is that there are some benefits and some disadvantages to using this kind of approach. So the advantage is it's actually allowing you to use more data per time point. And this is good for a couple of reasons. So sometimes when we're looking at stratigraphic periods, we find that some of these periods have very few taxa. However, we know that there must be ancestral species in there. There must be more data. And so by using a time slicing approach, we're using the data that we know exists. We're using what we know about the phylogeny to kind of put as much data in as possible. This is also going to allow us to have more power to do analyses that look at things like drivers of morphological evolution, or things like looking at how climate links with disparity. We can do that much more easily if we've got a lot more data points in that time series. This is also particularly important where we have small places, small bins which have very few small bins which are at important time points which don't have very many taxa in them. So that was the kind of the methodsy bit, and then I was supposed to be having a little bit of an empirical dive into some real data, and I have managed to actually do something. I did warn Phil that this might just turn into me doing a dance because I hadn't got any results until about a day ago. So what we've done with this now is taken these 4 data sets, same data set that Graham was using as well. So we've got 4 different data sets, and I just want to say thank you to the people who wrote these papers, first for sharing all of their data online in a way that could be accessed really easily, and also for helping me when I had some questions. And just a bit of a plea to people, please do share your data. It helps people like us who are trying to develop new methods to have data sets that we can test. And also, if you're going to share data, it would be great if you could share phylogenies and matrices in formats that we can do something with. So in Nexus formats and tree formats with trees and things like that. The number of data sets I had to abandon because their phylogenies were all in PDF files was kind of embarrassing. But these 4 did have all of the data that was needed. So thank you to the authors of these papers. So again, this was a nice GIF of this is what I've been doing for the last couple of weeks whenever I've had a spare moment of time. All of the code for these analyses is available in our Markdown files. It's all completely reproducible. It's all on my GitHub site. Again, it's not completely finished yet, but it's all there if people want to have a look. We're trying very hard at the moment in our group to make everything 100% reproducible. We're not sure we're quite there yet, but we're having a good go. So because this is what I've been doing sort of semi-frantically, the results I'm going to show, I haven't had time to make nice graphs for you, so you're just going to have to enjoy these. I'm doing that terrible thing where somebody puts up a slide and goes, don't just ignore the detail, it's fine. But yeah, so don't do what I'm doing right now, students, basically. So got these 4 different data sets. On the y-axis here, I've got time of peak disparity in millions of years. And then along the x-axis, we've got these 3 different models for fitting the time subsampling. And so the reason that we did this analysis was just to see whether these different methods of time subsampling actually make a difference biologically to the questions that you might be asking or the conclusions you might be trying to get. And so what you can see is, although it varies a little bit between models, when we do the time binning using stratigraphy compared to the time slicing, the time bins are giving a much later disparity peak than these other methods. Now, I'm not saying that any method is better than the other at this point, but what I want you to notice is that if you were trying to make a biological conclusion about where peak disparity was in your clade, actually the choice of how you subsample through your taxa is making a really big difference to the results that you get out of that. So the subsampling method does matter, and perhaps is something that we should be thinking about a little bit more. People think a lot about the method they're using to estimate disparity, maybe not quite so much about the time. And then another example, again, a terrible figure here, but we're just looking at whether, so this data set, this is the Beck and Lee data set, this cuts across the KPG boundary, so across that mass extinction. So we're looking to see if disparity changes before and after that mass extinction. And again, the detail doesn't matter too much, but the blue is showing you where we don't see a significant difference, and the pink is showing you where we do see a significant change in disparity. And again, I'm not saying that any one method is better or worse, but you can see that the choice of method does quite strongly influence whether you get a significant result or not. So it might be something to really carefully think about when you're trying to test these kinds of questions. Okay, so my conclusion then is time subsampling and disparity through time also matters. It's not just the way that you estimate disparity. And so to round up then, this is the link to Thomas's R package, if anybody's interested in that. I also wanted to highlight that the British Ecological Society, in collaboration with Methods in Ecology and Evolution, have just published a booklet on how to make your code more reproducible. So if you are finding you're doing some coding in R or whatever and you're interested in that, this is all freely available online. I've also got a couple of hard copies with me if people want to grab a hard copy. And then finally, I said I would advertise this meeting, which is again joint with the British Ecological Society's macroecology group, being organised by Alex Dunhill, Emily Mitchell and Erin Sorp. As this is going to be at Leeds in August, looking at the links between paleontology and ecology. So hopefully see some of you at that. Thank you very much.